In today's lesson, we'll be looking at indices. More specifically, what are indices and what are the laws that come associated with those that allow us to perform operations with indices. Okay, first things first. Here we have index laws and properties. The first thing we need to be able to know is what is an indice. Here is an example of an indice. 3 to the power of 2, 3 squared. So first off, we need to be able to label the components. The base of this indice is the 3, and the index, power, or exponent, it is called many things, and each question tries to trick you and use those different words, so we need to be aware that it does have 3 names, is the little number up the top. Now, what that little number up the top is trying to say is that this is the same as saying 3 times 3. So it's saying that this base of 3 is being multiplied by itself twice. So we have 3 times 3. That should all just be a little bit of revision. What we are more concerned with in this course is these index laws in our little red box here. So going through them one by one. Okay, so this first one here in blue says that any base to the power of any number multiplied by that same base to the power of another number, all you simply do is rewrite the base and add together those two powers. Our next indice law is the division. If you have some base to the power of something divided by that same base to the power of something else, all you simply do is subtract those powers and the base remains the same. If you have, here in red, any base to the power of anything, then to the power of something else again, you simply just multiply those powers together, the base remains the same. And the last one is a collection here on the left. Some people don't recognize the fact that you can have 2 bases in the same question. So here we have an A and a B, and they are both to the power of n. So we need to make sure that both the A and the B have the power of n when we expand those brackets. So there is 2 bases and 2 powers, even though that the powers are the same. Similarly, if you have a fraction inside a bracket, so we're talking about this one here, and that fraction is to the power of something, both the denominator and the numerator have to have that power applied to each of them separately to be able to successfully expand those brackets. 2 more on the side. One quick one, anything to the power of nothing is always equal to 1. And the second one, if you have a negative power, you can make that power positive by making the base the denominator of a fraction. So here we have a to the power of negative n. We made that n positive by making the am the denominator instead of being the numerator as it is now. Okay, some quick basic examples of these. The first one, 7 cubed multiplied by 7 to the power of 4. Those 2 bases are the same, so we are allowed to use our blue indice law up there. The base remains the same, and we simply add those powers together and get 7 to the power of 7. A quick division one. If we have 3 to the power of 10 divided by 3 to the power of 3, according to our indice law, these bases are the same, so we can use it. The base remains the same in the answer, and we simply subtract those powers and get 3 to the power of 7. Quick one, we have 4 squared, and then that term as a whole is also squared. So according to our law up the top, underlined in red, the 4 remains a 4, and we simply multiply the 2 indices together to get another 4. Our last one, a quick example of the 2 base question. If we have 7x in the brackets, and the 7x is all being cubed, if we want to expand those brackets, the 7 is cubed and the x is cubed. It is very important to remember that the power applies itself to both terms. That should be enough on those basic examples. Let's move on to another indice law. Here we have a version of our negative indice. How, if we had one, we could simply drop it to the bottom of a fraction and that made it positive. What if your negative power was applying itself to a fraction? You can't simply drop a fraction to the bottom of a fraction. What we do end up doing is similar to dividing fractions by another fraction, is we flip it And that is the same process that is being explained here, circled in green in our little red box. Is if we have a fraction to a negative power, we can simply just flip that fraction, the negative power disappears. Here, in our second example, it is the same thing, however the power is no longer 1. Remember, anything to the power of 1 is just itself. We have a fraction a over b having a negative whole number value that is not 1 applied to it. So we have to flip that fraction, but the power itself doesn't go anywhere, it just turns positive. So the n is still there, and if we wanted to carry that on, we could expand those brackets of this one here by having b to the power of n divided by a to the power of n, using another indice law that we just learned. A couple of quick examples using those little laws. We have 3/4 to the power of -1. We can simply just use our first indice law, circled in green there, and flip the fraction. Nothing else needs to happen. Okay, in our next example, we have 2/3 all to the power of -2. So the indice is no longer just a 1, so we cannot just flip the fraction and be done with it. We still can, however, flip it. We get 3/2. Because we flip the fraction, the power is no longer negative, and it just becomes 3/2 all squared. The question states to evaluate if possible, which means if there's brackets, get rid of them. So here we are, we're going to separate this one out and have 3 squared over 2 squared, which is going to leave us with 9/4 as our simple answer there. In our last example, it's getting a little complicated. We have a 5m divided by k cubed, all to the power of -3. Okay, we have a -3 on the outside, so we are allowed to flip our fraction in the brackets to get rid of that negative. We're going to end up with k cubed divided by 5m, all to the power of 3. So that's just the first step. The next one, to evaluate this question, we need to expand those brackets and apply that cubed on the outside to both the k and the 5m. So we're going to end up with k cubed and cubed again, divided by 5m cubed. And that's how we expand those brackets there. I'm going to give myself a little bit more room. Okay, next line. Remembering the index law of if you have something that has an exponent that is then given another exponent, you simply multiply those together. So we have k to the power of 3 times 3. On the bottom, when we are expanding powers on the outside of a bracket that has multiple bases, both the 5 and the m need to have the cube applied. So we're going to end up with 5 cubed and m cubed. Giving myself a little bit more room again. Okay, k to the power of 3 times 3, which is 9. 5 cubed. The question has asked us to evaluate, so we need to grab the answer for that, which is 125. And m cubed is as good as it gets. And there we have it. We have simplified this original question up here. 5m divided by k cubed, all to the power of -3. We've gone through the steps. We have ended up with k to the power of 9 divided by 125 m cubed. Even though this answer is longer, we are going to say that it is simpler. When things do not involve brackets, they are easier to work with. Next example. Here we have some quick examples of all the index laws that we've just learned. So 5 to the power of 7 divided by 5 to the power of 4. When those bases are the same, we are allowed to just simply subtract those powers from one another. So we end up with 5 to the power of 3. Next example. We have 3 multiplied by 7 to the power of nothing. Remember that anything to the power of nothing is simply 1. So we have 3 times 1 to give us 3. Next example. We have a half to the power of -2 plus 3 squared. So we're going to have to clean up this first before we can actually add those numbers together. So negative power means we can flip. So it becomes 2 over 1 all squared, plus 3 squared is 3 times 3, which is 9. Okay, we have a fraction that has its own index on the outside of the brackets. So if we want to expand that, we need to remember each both the top and the bottom have to have the index applied. So we have 2 squared divided by 1 squared plus 9. 1 squared is 1, so dividing by 1 is not going to change our answer. 2 squared is 4, plus the 9 leaves us with 13. And that's it. They're a quick little example of our index laws that you need to be able to use, not just on their own, but in any kind of given context that may come up in our exams. Okay, good luck, and I hope you enjoyed the video.